Okay, good afternoon, everyone. So let's start. So we have finished our first machine learning algorithm, decision tree. And as you may have noticed, homework 1 has been released last Friday. So we have about 16 days to finish homework 1. So I believe the time is pretty sufficient. But I would like to still suggest you to start homework as early as possible because you're required not only to solve problems on papers, but also implement decision trees, debugging, and show they work on real data sets. So if you have any issues about the algorithms, welcome to the office hour, and we would like to help you. But please be aware, it is your responsibility to implement an algorithm, debug a program. So we're not able to help you debug your program. So where the prerequisite is assumed, you should be able to implement an algorithm by yourself. And debugging, you cannot like throw a laptop in front of me and say, Professor, I don't know why there's some segmentation default. I don't know either. Right? You should be able to do it by yourself. And also, someone may feel inconvenient when you do not know what kind of APIs or libraries to process for data processing and loading, right? How to deal with the strings, those kind of steps. I'll give you a suggestion. I cannot memorize those APIs as well. Just Google it. All the recommended languages like Python, R, and MATLAB have huge communities in the web. I'm pretty much sure as long as you Google it, you can find whatever answer for your questions. Okay. Okay. So today we are gonna give a gentle tutorial, a gentle introduction to the computational learning theory. So don't worry, we won't dive into the theoretical steps, but to be a good practitioner for machine learning, you should know the key concepts and key ideas in its theoretical foundation. That is computational learning theory. You should know what is generalization error, what is empirical error, what are the key questions the computational learning theory want to address, and what does those theoretical bounds mean. And knowing this can help you or guide you to choose the appropriate learning algorithm, or even give you a better hint to design more powerful learning algorithms. So here, we'll just introduce the basic framework. What is the most important concepts? What is path learnability? And when from time to time, as the semester proceeds, when we discuss different types of machine learning algorithms, like organic machines or other learning algorithms, we'll go back to this topic and mention what kind of theoretical guarantee do we have? What does it mean? So next time when you develop a new algorithm, you can first search for the literature. Right? What kind of guarantees do we have? So we'll discuss 3 topics. First, we'll briefly introduce the general framework. Introduce key concepts here. What is the empirical error? What is the generalization error? And given the 2 types of errors, what is the goal of computational learning theory? As you will see, actually, key question is to estimate or infer the generalization error using empirical error. And we'll explain why. The major reason is that the generalization error is really infeasible to obtain. And then we'll describe what is the PAC framework. PAC is short for probably, approximately correct. And why should we define such a seemingly weird framework? Why we should incorporate probably approximately correct rather than definitely correct. And then what is PAC learnability? And what's the key points in the definition of PAC learnability? And finally, based on those definitions and framework, want to make some formal connections to the Occam's razor principle. Right? We discuss it in the context of the of computational learning theory. We can justify this principle in some degree. So again, this is a principle, not some theory or truth. So we cannot find a proof, but we can justify it in some way. Okay. So to introduce the basic framework for computational learning theory, and let us step back and look at the bigger picture. So our primary focus is supervised learning. So the key ingredients to conduct supervised learning include instance space. Right? Instance space are the set of entire instances in our supervised learning test, and label space consists of all possible labels we might predict, right? And hypothesis space. So hypothesis space are all possible candidate functions from which our learning algorithm will search over. You can consider as a kind of range of family. And our learning algorithm is to identify one particular function from a hypothesis space. So the three components in supervised learning. Right? And then to conduct supervised learning, we need to prepare a set of label data, which we call the training data. And we need to develop a learning algorithm. The input of this learning algorithm is the training data, and the output is some learned function. And here we also call it hypothesis. That is one element in the hypothesis space. So once we identify this hypothesis, which is denoted by small h, we can use hypothesis to make prediction on some new example. So this is a brief.
Is the new example considered test data?
Yeah, of course.
And does that test data include an instance space and a label space?
Latencies.
The test data, does it have both instances and labels, or is it just instances?
That's a good question. So if you want to apply the graphic problems, in most time, you don't have the labels for the test data, right? So you actually just give a prediction. But you trust your learning algorithm is reliable after the training phase, so you can use the prediction. But to verify the performance of your learned hypothesis here, right? So of course you need to give me some kind of evaluation results. For example, test accuracy. Then you need to collect a small set of data to just calculate the performance. So you see the difference here?
So basically, when you have the test data, you put it through your new model, and that's going to give you your label space.
The model is hypothesis. The hypothesis is actually in the hypothesis space. But the prediction, that is the predicted label, is inside the label space. Any question, I think? General framework for supervised learning.
So just one more. So an example could be, for your test example, you could input test data that has both instances and labels, and then you compare those labels to the predicted labels, and that gives you the accuracy.
Yes. Yes. Okay. So under this general framework, we discuss specific learners, right? So decision trees. That's what we have just gone through. And as the lectures proceed, right, we will discuss more specific learners, such as perceptions, least mean squares, small back machines, and so on. And we also, under the context of decision trees, we discussed several general ideas. See what is overfitting, right? What is feature representation, and the machine learning. In the machine learning context, actually, the instances are usually represented by feature vectors. So now, given the supervised learning, right, we would like to say, what does computational learning theory concern about? What kind of question the computational learning theory aims to answer? So first, we assume there is a supervised learning model, which is trained on a fixed training data set. And then, after the training, we just deploy our learning model in the wild. Then here is suppose we have done this, right? We have conducted our supervised learning test. And we are curious about how well will your learning model perform on future instances. That's the key question, or the core question the computational learning theory want to answer. So now to answer this question, or to formally study this question, allow me to introduce a few notations first. So we use big X to represent the instance space, right? And we introduce the concept space C. So concept space C basically just indicates the particular type or the family of target functions. Say if your target function, if you know a target function is kind of a balloon function, then the concept class C is just the set of all balloon functions. If your target function is just a linear function, then your concept class C could be like set of all possible linear functions. So basically, it just indicates the type, the class of the target function one. Why? Because the computational learning theory usually are not only interested in one specific learning algorithm to learn a very detailed target function. Instead, we want to know for a type of target function, can we have an effective and efficient learning algorithm, and what kind of accuracy can we get? That's why we introduced this concept class C. And then hypothesis space, we mentioned this many times. Basically, it's just the set of all candidates of functions, and our learning algorithm is actually a search procedure over the hypothesis space. And to conduct supervised learning, obviously, we should prepare the training instances. Right? So each training instance is a pair of the input vector from the instance space and its true label, which is assumed to be the output of the target function f. Right? This target function f is really unknown. We want to estimate this target function. And what we want is that, can we design a learning algorithm, or develop a learning algorithm to find out a hypothesis, small h, that belongs to the whole hypothesis space, such that the prediction of our hypothesis, learned hypothesis, is the same as the prediction of the target function. So to check or to verify this point, we usually check two questions. So first, we want to check whether the hypothesis ensure that for every input that belongs to the training set, the prediction of our learned hypothesis is consistent with the target function's prediction. This actually relates to the training error. Right? So basically, we want to ask what is the prediction performance on training set volume of our learned hypothesis. And next, we want to generalize it. Right? We want to say, okay, so now for any or for arbitrary input from the instance space, do we still have our learned hypothesis to have the same prediction with the target function? This relates to the generalization performance. And a reasonable assumption is that we assume the training instances are random or generated through some fixed but unknown probability distribution over the instance space X. Why is this reasonable? You can imagine, say, my task is to recognize human faces from images. And then what is the instance space? Yeah. all possible images, right? And your label space would be like +1, indicating this image is a human face. Otherwise, it's not a human face, right? So actually, you have no idea about like, all possible images all work, right? Or in the web, you have no idea. And there's some randomness because if you want to like collect some training images from some website, right? So today you might collect 1,000 images. Tomorrow you collect another set of images. The training set could vary. So there is some uncertainty in the training data. And so now that with some randomness, we can assume the training instances are sampled from some unknown probability distribution. But be aware, this probability distribution could be very complicated. And usually you cannot be optimistic that you think you can estimate this probability distribution. It's very likely that the probability distribution even does not have an analytical form.
Sorry, I'm still a little bit lost between what's the difference between the concept and hypothesis space? They're both functions, is that right? Hypothesis spaces.
Yeah, you can consider hypothesis space. Each hypothesis is a function. It's a matching between the instance space and the label space. You can consider like your hypothesis space is just the set of all linear functions, right, or quadratic functions. And your learning algorithm wants to find out or identify one specific function that fits the training data best. This is essentially a search procedure, right? So your concept class will indicate the type of the target function. But that's just some notations. You don't necessarily worry too much about those. We define this notation just for convenience of our discussion. Any questions so far?
So we're just assuming they're deterministic functions?
Yeah, we assume there's deterministic functions. And remember, the randomness comes from the data, not from the mapping. Of course, in the more advanced topic, machine topics, we can try to learn some probabilistic functions, but it's not the scope here. Okay. Any questions? Okay. So now, given those notations, let us define a generalization error. So what is generalization error? Given a data distribution D over the examples, that is over the instance space, and the generalization error of a specific hypothesis H with respect to the target concept F is defined like this. So basically, it's a probability that given the test sample is sampled from the data distribution D, the prediction of the hypothesis is inconsistent with the prediction of the target function. So it's just the probability that your prediction of hypothesis is different from of the prediction of the target function, given the test data is sampled from the data distribution D. So that's the definition of the generalization error, and they also refer to as true error. This is our goal, right? So we wish we can design a powerful learning algorithm such that this generalization error could be close to 0. But unfortunately, this is really invisible. But you should keep in mind, this is our golden standard. It's our golden standard. We want the generalization error to be as small as possible. So to give a concrete view about where the generalization error comes from. So assume this is our instance space. We draw a big rectangle to include all the possible instances. And the positive examples or positive instances labeled by the target function f are shown here, blue ellipses. So now suppose we conduct our learning algorithm and obtain a hypothesis. That is, we learn a hypothesis from a hypothesis space H. So due to the discrepancy between the target function and the learned hypothesis, so the label positive examples by the hypothesis H could be different. Here, another ellipsis. So now who can tell me where does the error come from? Yeah, two sides, right? So the error comes from, the generalization error comes from where F and H disagree. So in addition to the generalization error, we often evaluate our learning algorithm by another metric called empirical error. So let us just read this long sentence time, and then let me summarize this definition by just 2 words. So the empirical error is opposed to contrast to true error. So for a target concept F, the empirical error of a specific hypothesis H is defined for a training set S as a fraction of the examples in S where the function F and H disagree. So basically it means training error. So basically, if you want to do the empirical error, you just use your learned hypothesis to predict examples in the training set and just calculate the ratio or the fraction of making mistakes. Of the mistakes, you get the empirical error. And we denote the empirical error with this subscript S, and we denote the generalization error with the data distribution D. So now, with the empirical error, or in other words, training error, and the generalization error, we can redefine the overfitting, the concept of overfitting. Right? So when the empirical error on the training set is substantially lower than the true error, the generalization error, then we can consider this is a symbol, a warning that the algorithm overfits the training data. Right? We discussed last lecture, right? We give another, more clumsy definition about overfitting, right? When we say your algorithm is overfitting, you learn hypothesis H, and there exists another hypothesis H prime such that the empirical error of H is smaller than H prime, but the generation error is bigger. So now we can just use this more succinct definition. Right? Just whenever you find that your empirical error is much smaller than the generation error, that means you fit your data set, you fit your data too good, such that the noises in data set mislead your learned model, such that it performs better in the future test examples. So now with the introduction of the empirical error and generalization error, let us just supplement the notations.
Let me just make sure I understand. Empirical error is
the training error.
What?
The training error.
Inside the training. Whereas general error.
Yeah, general error
is just outside of training. Further.
I wouldn't say it's outside training. You can imagine, okay, all the instance space, right? All instance space, in entire instance space. And if I use all the instances in the entire instance space to make a prediction, what is the error? Right? But why should we emphasize there is an underlying data distribution D over the entire instance space? Because in practice, the entire instance space is really infinitely large. So you have numerous number of training examples. You have numerous examples. You cannot enumerate all possible examples because it is not finite. So we use a probability distribution to measure the distribution of those samples and define generation performance with respect to the data distribution. Yes. Of course. It must be data dependent, right? So you have a different training data. No, not have. You have different data distributions. Obviously, it will affect the generation error. Anyone still feel a little confused about this? Okay. And the key point is that for empirical error, you can imagine this subset of training data, right? It's just a subset of entire instance space. Of course, each example inside X is also sampled from the data distribution D, but it is finite, right? So you can imagine this error is just kind of an estimation of the true error. It's just estimation. It's not the accurate value, because this is essentially an expectation. If you rewrite this as kind of an indicator function, this is an indicator whether hx is not equal to fx. Right? So this is actually an expectation over the indicator function. And if you write down this error, it's actually this estimation for the expectation. That's fine. That's totally fine if you do not see this, because I need to write down the formula here. But why not? Let me just write down to make it more clear. Anybody see here? Okay, so this is true error, right? Which is the probability that when the past example sampled from data distribution D, whether the prediction is inconsistent with the target label, right? So if you define this is an indicator function, so remember this is just 1 or 0. So this is an indicator function. And the probability that hx is not equal to fx is actually an expectation. When x is sampled from the data distribution D, this indicator function. Does it make sense to everybody? Okay. This is just a binary error. When you sample x, you calculate it is either 1 or 0. And now I just rewrite this just as a binary variable. So the probability of binary variable is just the expectation of the binary variable. You can consider this is just a Bernoulli distribution. And now if you look at the training error, right? So what is the training error? It's just suppose your training set is have n samples, right? So it's just to test whether for each training example, the prediction of our hypothesis is not equal to the prediction of the target function. You see this? This is an equivalent definition of the training error. You just count the number of ones. If you make a mistake, you count 1, right? You go through all the training example, you say whether how many mistakes you made, and divide it by the total number of examples, you end up with the training error. So now, if you connect the two definitions here, what can you observe? if you take expectation over here, what is it? Remember, each xi is sampled from the data distribution as well, right? So this is a random variable. Xi is a random variable. So this indicator function of xi is random variable as well. So the training error is essentially a random variable. Now, if you take expectation, what is it? Yeah, this is true error, right? This is true error. This expectation over this same indicator function. It's not. You see what I mean, right? So essentially, the training error is kind of an estimation of the true error. Okay, someone looks, so face is good, feel comfortable. Someone still confusing. So if you still feel comfortable, come to the office hour or come to the TA.
When you take the expectation of the training error, wouldn't it be still an approximation of
No. It's not approximation anymore. If you take expectation, so you have n expectation over here, over n is exactly the same as the 12.
But you're still a subset of
That doesn't matter. That doesn't matter because when you take expectation, actually it goes through all the instance space. Each xi comes from the data distribution D, right? So if you take expectation, it is equal to say that I sampled numerous sets of training data and take an average. So actually you go through all the instances in instance space. So this is just some review of the basic statistic knowledge. And if you still feel uncomfortable to that, and just come to the office or later. Later when the lecture is ended, come to we can discuss later, right?
just one more question. So we can only really use the training error as an approximation if we make sure that our sample space is like a random enough sample inside the distribution, right? Our sample distribution should match the true distribution.
Yeah, very good. Yeah, you are right. That's our basic assumption. We must make such an assumption. We can carry out the computational learning theory research. Otherwise, we cannot see anything. But this assumption is definitely reasonable. Like if you do whatever, like learning task, of course you collect the training set, and if in the future you test them on the same kind of training set, you must assume there's some consistency in the data generating mechanism. Otherwise, it's not reasonable. It's not reasonable to conduct learning algorithm. So why should I do learning? I expect the future is kind of similar to the current situation. Otherwise, why should I learn? Any other questions? Okay, good. So if you still feel unclear, later when this lecture is over, come talk to me. So again, this is the notation list: X instance space, D unknown distribution, unknown data distribution over the instance space. F is unknown target function, which wants to find out the target function or find out close approximation to that. And H is a hypothesis function, where our learning algorithm search or find in the hypothesis space. And S is denoted, S denotes the M training examples, and error D, the true error, namely the generalization error, and S, the empirical error. That is the training error. So given those settings, here are a list of questions in the computational learning theory. So first, can we describe a bound the generalization error given an empirical error? So why should we do that? The reason is that the generalization error, although it is a golden standard, it is really feasible to get. The reason is because the data distribution D is really unknown. You don't know what is the data distribution. Can you write down a distribution form for for all the images in the web. It's not possible. Right? So can you like estimate the probability generative procedure for all the tweets in Twitter? Even Twitter cannot do that. Of course, due to the randomness of data, you can safely assume they are governed by some random distribution, but you will never know what is the specific distribution is. And then, now that you don't know the data distribution, you cannot compute the true error. Why? Because the true error is determined by the data distribution. So, in practice, how can we do that?
Grab a large enough or sample set and then take a subset of that and keep it off to the side and compare against like an actually train on that.
Yeah, exactly. Exactly, right? So what can we do? We just sample a bunch of test examples from the data distribution and then calculate the error, right? But this is just estimation. This is always estimation. It's not accurate. It's not the exact generation error. And to ensure your estimations to be close to the true error, right, you need to use a lot of examples, huge number of examples. So it's computational cost. Then the computational learning theory wants to infer the true error by only using empirical. Empirical error is always easy to get, right? Because the set of training data is always finite. When I conduct learning algorithms, I can always get the exact empirical error. The question is that can we use empirical error to infer or bound the generation error? We do not need to carry out expensive tests. So the second question would be, is a particular type of target function learnable? And further, we would like to ask, what do you mean by learnable? So ideally, we won't say, okay, I want to accurately identify the target function. But it turns out infeasible in practice. You don't know what the target function is. You even cannot ensure. You even cannot say for sure this is the target function. And the third question would be, how many examples does an algorithm need to guarantee the good performance? This is also called sample complexity. So consider you have developed a very effective learning algorithm. But it turns out to reach a very good performance, you have to use 10 billion or 1 trillion examples for training. No one will use it. It's too costly. So we need to characterize sample complexity. What kind of sample complexity is acceptable for practical learning algorithm? And finally, how much cost does an algorithm take to learn some specific type of target functions? This directly relates to the computational complexity. Right? No one will like our learning algorithm to be empty hard, to run some data and never ends. So to answer this question, we need to first define in what kind of degree a learning algorithm is satisfactory. So what is the measurement of the goodness of the learning algorithm? So let us first consider the question. So can we expect a learner to exactly capture the target function? Always. Can we expect that? Why? Just approximation. Yeah, just approximation to that function. But do you have any reason to justify that? Why we can only find an approximation to that function? Let us just assume that your learning algorithm is very powerful and hypothesis space is large enough to include all types of target functions. Can we expect that?
exact perfect data set. So I was expecting an exact functionality.
That's a very good point, and it's very close to the reason I want to show you. So the reason, a direct observation, although there are many other reasons, but a direct observation is that there are uncertainty in data, as you just mentioned. The training data are always finite, and the instance space are usually infinite. That means you cannot cover every single point, single instance in the instance space. So even you have a very powerful learning algorithm, very powerful, but what if the quality of the training data is bad? It is very unlikely that you can identify the exact target function. Right? Of course, when the training data is large and is sufficient and comprehensive, it is possible. It's possible you identify the target function. But in many cases, due to the infinite amount of the instances in the entire space and limited computational resources, you can only sample a subset of data with respect to some unknown data distribution D. You can never make such kind of guarantee. And in addition to that, even for the same set of training data, there could be multiple hypotheses. They are all consistent with the data, meaning that their training error are all zero. In this case, you only have the training data. You don't know which one should be the target function. Right? You cannot differentiate. And again, because we do not know the unknown data distribution, the data distribution is unknown, it's complicated. So you have an uncertainty about labels for future examples as well. Because you never know the examples, you won't know the labels as well. And especially when the training set is not comprehensive enough, meaning that there are some uncommon examples which do not show in the training set. Remember, the learning algorithm aims to fit the training data to be as good as possible, right? So as a trade-off, it is very possible that those uncommon examples that do not appear in the training set is misclassified by the learning algorithm. So you'll never be able to ascertain that your learner is perfect to capture the exact target function. And even worse, you cannot always expect to learn a close approximation to the target function. Why? Because of the training data. The training data is essentially kind of random variables. If your training data is good, this time you sample a very good training data set, then probably the learning algorithm can find a close approximation to the target function. But what about next time? We'll collect a bunch of very bad training examples, contain a lot of noises. Then your learning hypothesis could be far away from the target function. Those are practical reasons. So then, if we still want to conduct the computational learning theory, we should give a more reasonable or realistic definition regarding how a learning algorithm, a learner, is satisfactory. In such kind of case, we should incorporate the probability. So we expect that a good learner, a learning algorithm, can, with high probability, learn a close approximation to the target concept or target function. With high probability means that we tolerate the bad cases, which are due to the bad training data sets. That's the way we measure whether a learning algorithm is good enough. Does it make sense to everyone?
What in general in this field is considered high probability?
What?
What in general would be considered a good high probability correlation?
Yeah, that's very good. But just I will give you very detailed definition in the next slide. But just want you give you a sense, right? You cannot like deterministically conclude that the learning algorithm is good or bad because the uncertainty in the data, right? So in a realistic way, if you want to conduct some theoretical research, we need to relax our expectation. Then our expectation is defined in this angle. That is, we will hope a good learner will have high probability to learn a close approximation to the target function. And with respect to in regard to what do you mean by high probability and what do you mean by close approximation? Right? This is the definition. Probably approximately correct. That's where it comes from, right? So first, to design or to define what is high probability and to define what is close approximation, we introduce two parameters, epsilon and delta. And we say a good learning algorithm can with probability at least 1 minus delta. So remember, delta is small, right? So 1 minus delta means that high probability or high chance, right? And the learner can produce a hypothesis with error at most epsilon. So epsilon indicates the true error level, right? So at most epsilon means that it is close to the target function. Of course, the true error of the target function is 0. But here, when we want to measure its closeness, we introduce this error level epsilon. So overall, the definition is that we think a satisfactory or a good learning algorithm should be probably approximately correct. That is PAP. And it means that given some specific epsilon delta, this learning algorithm can return a hypothesis with high probability, at least 1 minus delta. Its true error at most epsilon won't exceed epsilon. This is the definition of the path.
So how exactly calculate delta?
No, there's no way to calculate delta. You need to specify epsilon delta. That's kind of parameters you want to measure the goodness of this algorithm. So like I give epsilon to be like 0.1, delta like to be 0.01. If some algorithm can satisfy this, I say, okay, this algorithm is probably approximately correct at error level being 0.1 and confidence level at like 0.01.
So then how do I show that this algorithm gives that delta for some given hypothesis class?
That's a very good question. That's the whole topic of conditional learning theory. There's a lot of techniques, mathematical techniques. Of course, most of them are based on empirical systems. Okay, hopefully everyone is comfortable with this similar weird definition. I don't like this definition because it's too long, but it turns out to be the most realistic measurement for a practical learning algorithm. And as some of you have mentioned, right, the underlying assumption for us to hope a learning algorithm to be a hack is that we assume the data distribution for training and test are consistent. You can imagine if the learned hypothesis performs well on the training set, it should also perform well on another test set underlying the same data distribution. And this assumption is pretty reasonable. Whenever you conduct a supervised learning algorithm, of course, you will assume like the training data are generated from the same distribution as in the test data. So, given the definition of probably approximately correctness, right, we define path learnability. So this is a very important concept in pack learning framework. So basically, what is pack learnability? It just want to define whether a type of target functions is effectively and easy to be learned from some specific learning algorithm. So if some kind of some type of target function is too hard, then it might not be pack learnable. So now let us look at the definition of pack learnability. So consider the concept class C. Remember, the concept class just indicates the family or the type of target function over some instance space X, and we have provided a learning algorithm L with hypothesis space H. We say this type of target function, say, is pack learnable by the learning algorithm L if all this satisfied. So what kind of conditions we must satisfy to conclude that say is pack learnable by L? First, if for arbitrary target function in the class C, and for arbitrary data distribution, remember this is very strong conclusion. That means we do not restrict the data distribution. For arbitrary data distribution over the instance space, and for arbitrary setting of epsilon and delta. So epsilon and delta are all the error level and the confidence levels. Our learning algorithm L can use M examples. Those examples are sampled independently according to the data distribution D, and the learned hypothesis will have high probability, that is at least 1 minus delta, to find out to pass the true error at most epsilon. And meanwhile, the number of examples should be polynomial to these four numbers: 1 over epsilon, 1 over delta, n is the number of features, and the size of hypothesis space. So it looks a little tedious, right? So let us look at it again and summarize. I translate it into a more friendly definition. So basically it says that if the concept class C is pack learnable by some learning algorithm L, if with only polynomial numbers of training examples to these four numbers, our learning algorithm can find out the hypothesis which has high probability to obtain a good hypothesis. The true error is less than, is at most epsilon. That's pack learnable.
So I'm a little confused what you mean by n is polynomial instead of numbers.
N is polynomial to what?
You're saying n is polynomial and the set of numbers one versus one.
Yeah.
Exactly.
Polynomial means that, okay, so you know the big O notation, right? So polynomial means the M can be represented as big O over a polynomial of the four numbers. So you can imagine there should be epsilon to the power of what, like to 3 or 1 over 2, power to 4 or whatever. But at least it should be polynomial to that. It could not be like exponential to 1. This is not polynomial. Polynomial usually means its complexity is acceptable. And recall that the true error, the definition of true error here, is the probability that the prediction of a hypothesis is different from the true label.
So you can only determine if something, if a problem is pack learnable by building the entire system and running these tests, and like defining epsilon delta value. You can't like define just figure that out beforehand. You don't waste all your time.
You mean the definition or examining whether it's pack learnable? Well, I mean, you're asking a question regarding the definition, or
Well, just in general, like if you had a problem you were presented with that you wanted to determine if it
you have to, if you wanted to actually determine the path learning, you have to go through this rigorous process. And
Oh, okay.
you know what I mean? Like, you can't approximate beforehand in some way.
Well, that's a good question. So you asked a question regarding how to check whether an algorithm is path learnable or not, right? So of course, if you want to like check it through the definition, it will be not realistic. It will be not practical. But there are many other theories that use other, more practical methods to check whether your algorithm, your learning algorithm is path learnable. Can path learn some particular type of target functions. But here, we're not going to discuss those kind of steps, but I just want you to know what is path learnability and where does the path learnability wants to express. That's what we're going to discuss in the next slides. What's the key points in definition of path learnability? So any question in regard to understanding this sentence, tedious sentence?
I just want to make sure that I understand it, so can I repeat it back? So that something is an algorithm is path learnable if it only takes polynomial examples.
To this for practice.
With respect to epsilon and stuff. To learn the target function within epsilon with the likelihood of 1 minus delta. Okay. So I don't necessarily get the with probability at least 1 minus delta. What is that relying on?
So as we previously mentioned, right? So you can now say I can always learn a hypothesis whose trial is less than some epsilon. Why? Because you have no idea what is the quality of the training data. So there are uncertainties in the training data. So when you say we want to justify a learning algorithm is good, you can now say, well, my algorithm guarantees you that 100% sure you can reach a generalization error less than 1%. It's not possible. If I give you a garbage of training data, a garbage in, garbage out, it is unlikely for you to get. So then what kind of theoretical measurement can we choose? I can only say, okay, reliably, I can only say, okay, with very high chance, with 99% chance, my learning algorithm can give you a learned model with true error less than 5%. Does it make sense?
How are we supposed to measure that likelihood that our learning algorithm will be given garbage data?
That's a good question. So that depends on how your data distribution is. Right? So basically, we assume the training examples, test examples are sampled from the same data distribution. Right? Of course, the data distribution could contain some noises. And you can imagine these noises are not uniform. So this time you sample a set of training data with like little noises that is possible. But next time you might sample another data set which full of noises. Remember, noises are random variables as well. So those noises, of course, can lead to different performance. The problem is that whether your algorithm is robust enough to like minimize the influence of the noises. So if you can like try to minimize to decrease the influence of bad influence from noises as much as possible, then you end up with a high chance to get good learned model or hypothesis every time. But you can never guarantee that 100% sure. Even if you feed me a garbage, I give you good learned hypothesis. That's the key idea. Why we should introduce the language of probability here to define the goodness for a learning algorithm. As to how those how those terms takes effect, we'll look into it through some detailed example. You will see it and you won't feel uncomfortable with that. But at least you should be aware. We should have some probability description here. Any questions? Okay, good. And then further, okay. And we can further extend path learnability to like efficient path learnability. So that directly relates to the computational complexity. So we can say if the concept we say that concept C is efficiently learnable, efficiently path learnable, if the algorithm L can produce the hypothesis with computation complexity also polynomial to these 4 parameters. So you see what is efficient path learnable? We not only requires polynomial sample complexity, we also require polynomial time complexity. Any question in the definition here? Okay, so yeah, so as I just mentioned, right, epsilon indicates the generation error, and delta indicates the confidence error. So now when we look into the path learnability, the definition of path learnability, we actually impose 2 limitations or 2 restrictions. First, we require the sample complexity should be polynomial. Why? Because polynomial degree really indicates tractability. The path learnability is an indicator to differentiate those hard to learn examples and easy to learn. Hard to learn target functions and easy to learn target functions. So path learnability means that we only use polynomial number of training examples, we can achieve some specific level of path, probably approximately correct. If the number of training examples, which are necessary to achieve the same level of path is exponential, then it won't be practical. It is not path learnable. So do you get it? That's one key restriction. And another restriction is about computational cost. We require the computational complexity is also polynomial to the 4 parameters here. That means that our algorithm should be efficient enough, even given a polynomial number of the training examples. And another starting point that you should be aware that path learnable requires that there must be a hypothesis with arbitrarily small error for every target function in a concept class. Why? Because to achieve path learnability, we must satisfy all settings for epsilon delta, all settings for the generalization levels and confidence levels. That means whatever epsilon delta, they can be extremely close to 0. You can always find out target function. You can always find out a hypothesis which has the true error at most epsilon. And in order to achieve the path learnability, we usually design an algorithm such that the hypothesis space contain the concept class. If the hypothesis space happens to be identical to the concept class, we call this is a properly path learnable. And again, path learnability is kind of worst case definition. Why? It requires the probably approximately correct is satisfied for every data distribution and for every target function. So no exceptions. So it's a very strong definition. So any Any question in regards to the understanding of the path learnability?
So I guess for both the polynomial sample complexity and polynomial time complexity, you kind of go over the axes. Would that be x-axis as time, x-axis complexity, or so these variables describe the polynomial shape?
Yes. You can imagine a polynomial function of these four parameters. Right? So, how many of you are not familiar with big O notation? Not familiar, unfamiliar with big O notation. I feel strange on that. You're good, right? So basically, the polynomial in parameters basically means that okay, this value can be bounded by a polynomial function for this. So again, I can imagine, okay, although I don't know what kind of m can make our algorithm to satisfy this probably approximate correctness, right? But I know this number of examples m must be less than or equal to some polynomial functions of the four parameters. That is meaning for polynomial in for this. Does it make sense? Yeah. Why we emphasize it must be polynomial in? Because that's the only the practical algorithm work. If it is exponential to these parameters, you can imagine like when you increase the number of the features n, or you just decrease epsilon to achieve a better generation error, and the number of samples will explode, right? Will explode, and then computation cost will be exploded as well. Any other questions?
Seems like it'd be really hard to prove theoretically for a given learner. So in practice, we approximate by grabbing some sample data and using some experiments, and most likely it's not learnable, rather than for sure this learner L is not learnable for all cases. Because you don't know a lot of the full distribution.
Yeah, you're right. You are definitely right. And during the research, we usually assume there are some properties with respect to D. So although we don't know like specific form, the analytical form of D, but we usually assume some properties of D. Say the distribution of shape of the D is kind of a long tail or whatever. Right? And also in theoretical research, we often make more ideal assumption with respect to D. Like you can assume like the data distribution is uniform over like the entire n-dimensional space, and what kind of result can we get? Although in practice, yeah, there could be some discrepancy, but those results have already been able to guide you to make decisions in practice. And also there are some more general results and without any assumption about D together. But those are too much detail in the computational theory. And the reason, the motivation I introduced this concept to you guys is to have you realize that why we would like to give this definition. This definition actually characterizes those more effective and easy target concepts, target functions. And to conduct some theoretical research, the first step is to differentiate or to classify the research objects. Which one are better, are easier, are more friendly, which one are harder. And regarding different types of objects, what is properties do we have? Okay, so now I have introduced path learnability, and all the basic components in computational learning theory. We want to use this few steps to justify Occam's razor first. So Occam's razor just says we want to prefer simpler explanations over more complex ones. Result never add or model complexity when unnecessary. So how do we justify performance reason? Let us consider a simple example. Assume we have a learning algorithm and search over a hypothesis space which is finite, not infinite. So this is actually not a practical case. It's just some kind of mind experiment, mind and ideal experiment. So suppose hypothesis space is finite, and our learning algorithm is powerful, such that the learned hypothesis is consistent with all the training examples. Meaning that as long as I was trained from M training examples, the learned hypothesis can have zero training error. Meaning that I can predict each training example 100% accurate. And now we want to claim that the probability, the generalization and performance of this learned hypothesis H bigger than some level epsilon is less than the size of hypothesis space H times 1 minus epsilon to M. This is our conclusion. So what does this claim mean? What does this conclusion mean? Basically, first, the learned hypothesis is consistent with all M training examples, meaning zero training error means that, okay, we found a good hypothesis, right? However, its generation error is bigger than epsilon. So it indicates that although hypothesis H is consistent with training, but it performs bad in future cases, in the generalization performance. This is exactly what we have discussed previously. Although my learning algorithm is good, I can even produce a hypothesis can correctly predict every training example, but the generalization performance is still bad. We want to know what is the probability this kind of case happens. So now we claim that this probability, the chance of this case that consistent hypothesis but bad in generalization is less than this. And you can imagine when epsilon is large, 1 minus epsilon is small, right? When we increase the number of training examples, this chance will be very small. But it does not mean this chance is zero. That's why we incorporate probability measurement in our pack definition. Yeah, the probability that the true error of H is bigger than epsilon is less than. So this proof is pretty straightforward. So I just give you a sketch. So suppose H is such a bad hypothesis and has a true error is bigger than epsilon. Right? And then for arbitrary example, test example, which is inconsistent with the prediction of the true target function, the chance is less than 1 minus epsilon. Why? Because the definition of the true error. The definition of true error is the probability that fx is not equal to hx. So now that we know the probability that fx is not equal to hx is bigger than epsilon, then the probability that they are equal is less than 1 minus epsilon. Right? This is just according to definition. And now, because the training set consists of m examples drawn independently, so we can imagine that H is consistent with m examples less than 1 minus epsilon to the m. Because each inconsistent probability is less than 1 minus epsilon, right? So you have m training examples, you just bound them by multiplying the upper bound together. You get 1 minus epsilon to the m. Any questions? Error false, right? And then now I want to say, what is the probability that there exists some bad hypothesis which is consistent with m examples here, right? And the generalization error is bigger than epsilon. That's exactly what is the probability. To quantify this, we simply use the probability equations. In equations we prove in the homework 0. Right? So this event that there exists some bad hypothesis in H, which is consistent yet bad, can be represented as the first hypothesis in H is bad and inconsistent, or the second hypothesis in big H is bad or inconsistent, or until the last hypothesis in the hypothesis space is bad and inconsistent. And this probability is what? Is less than what? Is less than what? Which is the probability of a union of events is less than summation of the probability of each individual events, right? So here, so the probability of each individual events is upper bounded by this, right? 1 minus epsilon to the f. So the probability of this whole event, which this event, is upper bounded by the summation of the bounds for each individual events, which is size of H times 1 minus epsilon to f. That is our conclusion. So now we have this conclusion, right? We know that the probability that there is a hypothesis such that it's consistent with all M-training examples, but its generalization error is unsatisfactory because it is bigger than epsilon. This chance is less than big H, the size of big H, the size of whole hypothesis space, times 1 minus epsilon to f. So obviously we want this chance to be as small as possible, right? If we find out if our learning algorithm is very powerful, and each time we can always find out a hypothesis which is consistent with all M-training examples, meaning that we have 0 training error. Of course, we want the performance of the generalization is good as well. Right? We don't want this happen. Then what kind of strategies can we use? What kind of strategies can we make this probability or this chance to be as small as possible? An idea? So you can imagine that a consistent hypothesis which is bad in generalization performance, the chance is bounded by this number, right? So now how can I decrease the chance? Yeah, exactly, right? 1 minus epsilon is always less than 1, right? So if you increase number of training examples, this bound is decreased, right? And then the chance that you have a bad generalization performance is low as well. Any question at this point? Okay, so I guess we're at time, and we'll continue to discuss that on Wednesday. So anyone still feel uncomfortable with the definition of true error and the interval error? Can come talk to me right now.